All right, buckle up everyone, because today we're diving headfirst into some seriously cool research.
Oh yeah, we're talking cutting edge stuff here, like the kind of stuff that makes you rethink what's possible.
Exactly. We're going to be exploring how to simulate those super complex systems. Like how crowds move or how traffic flows even.
Even down to the level of how molecules fold. It's wild.
Seriously. And all this is thanks to this paper we're looking at today.
Yeah, it's called LaM-SLidE, Latent Space Modeling of Spatial Dynamical Systems via Linked Entities.
Okay, gotta admit, the title's a bit of a mouthful.
True.
But don't let that scare you off. It's all about finding a new way to predict how systems behave when they've got tons of moving parts.
Like, imagine all the atoms in a molecule, or all the people in a huge crowd.
Yeah, or like cars in traffic, right?
Totally, that's exactly the kind of stuff we're talking about.
Okay, but how do you even start modeling something that crazy complex? Where do you even begin?
Well, one common way is to use something called graph neural networks.
Graph neural networks.
Yeah, GNNs for short. It's where you treat every entity as a node in a graph. So like each person in a crowd would be a node.
Gotcha. And then the connections in the graph show how they're all related.
Exactly. Like who bumps into who, who's moving towards who, that sort of thing.
Makes sense. But I guess even GNNs have their limits, right?
Yeah, definitely. They can run into trouble when you're dealing with thousands or even millions of these entities all interacting.
Oh, I see. So like if you were trying to model rush hour traffic in a mega city, GNNs might not cut it.
Pretty much. And they also struggle when you want to create completely new scenarios instead of just analyzing existing data.
So if you wanted to, say, simulate a whole new traffic pattern to avoid congestion.
Right. That's where GNNs start to hit a wall.
Okay, so that's where this LaM-SLidE method comes in, right?
Exactly. LaM-SLidE tries to do things a bit differently.
So what makes it so special? What's the secret sauce?
Well, it combines the good parts of GNNs with this super powerful technique called latent space modeling.
Latent space modeling. Sounds kind of mysterious.
It kind of is. It's this idea of creating a blueprint that captures like the essence of how the system behaves, but in a super compact way. It's like a cheat sheet for the whole system.
A blueprint. That's a cool analogy. But how do you even make a blueprint for something as unpredictable as a crowd of people?
Right, and that's where LaM-SLidE gets really clever. It uses the system of giving each entity in the system, like each person in the crowd, a unique ID tag.
Okay, so like giving everyone in the crowd a name tag or something.
Yeah, exactly. But then, get this, it randomly assigns those IDs.
Wait, randomly? Why would you do that? Does that make things even more chaotic?
It seems counterintuitive, right? But there's a method to the madness.
Okay, I'm all ears.
So by doing it randomly, LaM-SLidE can handle situations where the number of entities in the system changes. And that's something that trips up a lot of other approaches.
Ah, I see. So it's like having a blueprint that can adapt to buildings of different sizes.
Exactly. It makes it much more flexible.
This is getting more and more intriguing. But okay, so you've got these unique ideas assigned randomly. How does LaM-SLidE actually use them to make predictions about how the system will behave?
It all boils down to three main steps. The first one is what's called the encoder.
The encoder. Okay, what's that all about?
Well, the encoder takes all the raw data about the system stuff, like the positions and velocities of each entity, and compresses it into this much smaller, more manageable form.
So it's like boiling down a huge textbook into a few key bullet points.
Exactly. It's all about distilling the essence of the system's behavior.
I like it. Makes sense. So what's next?
Next up is the approximator. Now, this is where the real magic happens.
Ooh, the approximator. Sounds important.
It is. This is where LaM-SLidE actually learns the rules of the game, like the underlying physics or the social dynamics that make the system tick.
So it figures out the underlying patterns of behavior without getting lost in all the tiny details.
Exactly. That's the beauty of it. It works within that compressed latent space representation, so it's super efficient.
That is super cool. So we've got the encoder and the approximator. What's the last step?
The final step is the decoder. This guy takes the output from the approximator, those predictions it made in the latent space, and translates them back into real-world coordinates and properties.
So it's like taking that blueprint and using it to build the actual building.
Spot on.
Okay, so to recap, LaM-SLidE takes a snapshot of the system, encodes it into a super compact blueprint, uses the approximator to predict future states within that blueprint, and then the decoder translates those predictions back into real-world terms. That's pretty elegant. But the big question is, does it actually work in practice?
Well, to find out, the researchers put LaM-SLidE to the test on a whole bunch of different systems.
Ooh, and what did they try it on? But bill the beans.
Well, one of the things they tested it on was they started with something pretty relatable, pedestrian movement. You know, how people move around in those crowded areas.
Ah, so like trying to predict how people weave through a busy train station or a packed plaza.
Exactly, and they use this data set called EFUCI, which captures real pedestrian movements in those kinds of spaces.
Okay, yeah, I could see how that would be a challenge. All those people stopping and starting, changing directions. Did LaM-SLidE manage to handle all that?
It did, and get this, it actually outperformed a bunch of other methods that were specifically designed for pedestrian simulation.
Really? So it was better than the specialized tools? That's impressive.
It is, and then they decided to kick things up a notch. They tried using LaM-SLidE to simulate something even more complex, basketball players during a game.
Whoa, hold on. From pedestrians to basketball players? That's a pretty big leap.
It is, right? And for this one, they used the SportVU NBA movement dataset. It's this dataset that tracks the positions of all the players on the court, plus the ball, throughout an entire game.
Okay, now that's a lot of data, and I bet those interactions are crazy complicated. Did LaM-SLidE manage to keep up?
It's wild, right? But yeah, LaM-SLidE actually did really well. It was able to generate these super realistic simulations of how the players move, even predicting things like who would get the rebound or if a shot would go in.
Wait, seriously, it could predict whether a shot would be successful. That's pretty amazing.
It is, and the crazy thing is that they didn't give LaM-SLidE any specific basketball knowledge beforehand. Like, it didn't know the rules of the game or anything about player strategies.
So it was basically learning everything from scratch just by analyzing the movement data.
Exactly. It figured out the patterns of movement and behavior just from the data itself.
Okay, now that is impressive. It seems like LaM-SLidE is pretty adaptable. So what else did they throw at it? Did they try it on any other types of systems?
Oh, they definitely pushed it to the limits. To really see what it could do, they took LaM-SLidE down to the microscopic world. They used it to predict the movements of atoms in small molecules, like think aspirin or benzene.
Whoa, hold on. From basketball players to atoms, that's like zooming in a million times. How do you even track the movements of something that tiny?
Right, it's mind-boggling. For this, they used a dataset called MD17. It's full of really detailed simulations of how molecules move and interact at the atomic level.
Okay, so that's where they got the ground truth data. But I still can't wrap my head around how LaM-SLidE could handle something so different from the other systems.
I know, it seems crazy, right? But the amazing thing is that LaM-SLidE actually did a really good job predicting those atomic movements. And remember, the forces and interactions at that scale are completely different from those governing people or basketball players.
It's like LaM-SLidE can speak the language of complex systems, no matter what the domain. It can find those underlying patterns of behavior regardless of the scale or the specific details.
That's a great way to put it. It's almost like a universal translator for complexity. And they didn't stop there. They wanted to see what would happen if they gave LaM-SLidE more power, more resources to work with, so they decided to scale things up.
Scale things up. You mean they simulated even bigger systems, like a whole city or a giant molecule?
Well, not quite in that sense. What they scaled up was the LaM-SLidE model itself. They gave it more parameters to work with, basically increasing its processing power.
Ah, I see. So like giving LaM-SLidE a bigger brain to think with, did that lead to any improvements?
You bet it did. They found that the larger they made the model, the better it performed across the board. The more parameters it had, the more accurate its predictions became.
That's really cool. It's like there's this direct link between the model's size and its ability to understand and predict these complex systems. But it also makes me wonder, is there a limit? Like, could the model become too big, too complex to even manage?
Yeah, that's a great question. There's definitely a trade-off. Larger models do require way more data and computing power to train and run. And there's also this risk of something called overfitting, where the model becomes so good at fitting the training data that it doesn't actually generalize well to new situations.
So it's like a student who memorizes the whole textbook, but can't actually apply the concepts to a new problem.
Exactly. So it's all about finding that sweet spot, a model that's powerful enough to capture the complexity, but not so big that it becomes unwieldy or loses its flexibility.
This is all super fascinating. But let's bring it back down to earth for a second. Why should our listeners care about all this? How could this research actually impact their lives?
That's a really important point. This isn't just about some abstract theoretical stuff happening in a lab somewhere. LaM-SLidE has the potential to seriously change the way we understand and interact with the world around us.
Okay, I get that it's potentially groundbreaking, but can you give us some concrete examples? Like, how could this actually affect people's day-to-day lives?
Absolutely. Just imagine a world where we could accurately simulate the spread of a disease. Think about it. We could predict where outbreaks are likely to happen and figure out the best ways to contain them.
Wow, that would be huge, especially after everything we've been through in recent years.
It would, right. Or how about optimizing traffic flow in cities? We could use simulations to reduce those soul-crushing traffic jams and make commutes way faster and more efficient.
Now, that's something I think everyone can get behind. Less time stuck in traffic. Sign me up.
Right. It's a win-win. And it goes even further than that. Imagine being able to design new materials with specific properties. Like, what if we could create a material that's super strong but also incredibly lightweight? Or a drug that targets a specific disease with pinpoint accuracy.
Okay, yeah, now we're talking game changer stuff. That kind of technology could revolutionize so many industries.
Absolutely. And with LaM-SLidE, instead of just stumbling around in the lab hoping to discover these things by chance, we could actually design them on a computer first. We could simulate how they'd behave and then create them in the real world.
So it's like going from just observing the world to actually shaping it, designing it from the ground up.
You got it. And that's what's so exciting about this research. It opens up a whole universe of possibilities. It's like giving us a toolkit, not just to understand the universe, but to create entirely new ones.
That's a powerful image. It really feels like we're on the cusp of something huge.
We are. And there's one more really cool aspect of LaM-SLidE that I think is worth highlighting. It's this idea of not just simulating existing systems, but using LaM-SLidE to design completely new ones from scratch.
Wait, really? So instead of just predicting how things will behave, we could actually use it to create things that have never existed before.
Yeah, exactly. Like, imagine using LaM-SLidE to design a new type of molecule.
A brand new molecule, like a drug that targets a specific disease, or maybe a material that's super strong and lightweight at the same time?
Yeah, things like that. Instead of trying to discover them through trial and error in the lab, you could design them on a computer using LaM-SLidE and then actually synthesize them in the real world.
That's mind-blowing. So we could go from simulating reality to actually shaping it.
And that's what's so exciting about this whole thing. It's like LaM-SLidE gives us a set of tools to not just understand the universe, but to create new universes within it.
That's a pretty powerful thought, right? But out of everything we've talked about today, what was the thing that really stood out to you the most?
Good question. I think for me, it's got to be the versatility of LaM-SLidE, the fact that it can be applied to systems that are so different, like pedestrian crowds, basketball games, and even molecular dynamics. It's incredible.
It really is. It's like it shows that there are these universal principles underlying all these seemingly different phenomena.
And to me, that's just mind-blowing.
I totally agree. And I think what excites me the most is this potential to not just simulate existing systems, but to actually design completely new ones. Like we're moving from just observing to actually creating.
Yeah, and who knows what incredible discoveries and innovations are waiting for us in this new world of creation.
I can't wait to find out. This has been an incredibly thought-provoking deep dive. I feel like we've just scratched the surface of what's possible with this research.
Totally agree.
But for now, we got to wrap things up.
Aw, all right. But before we do, I want to leave our listeners with something to think about.
Okay, hit us with it.
So if LaM-SLidE lets us design these brand new systems from scratch, what ethical considerations should we be thinking about? Like, how do we make sure that these powerful tools are used responsibly and for the benefit of everyone?
That's a great point. Like with any powerful technology, we got to think carefully about the potential consequences, both the good and the bad.
Exactly. And it's not just the scientists and engineers who need to be thinking about this. It's a responsibility we all share.
Well said. We need to have these conversations about the ethics of this tech and figure out some guidelines for how to use it wisely.
Yeah, the future we create is going to be shaped by the choices we make today.
So true. And on that note, we'll leave you with those thought-provoking questions. Thanks for joining us on this deep dive into the world of LaM-SLidE. Until next time, keep exploring and keep asking those big questions.